Machine learning engineering often grinds to a halt, not during the modeling phase, but at the moment of deployment. This friction, the struggle to align specific library versions and hardware drivers across different machines, is known as dependency hell. This diagram shows the ecosystem required to run a standard model. You have specific Python versions, exact CUDA drivers, and a precise tree of pip libraries. When you attempt to lift this model from a local developer laptop and drop it onto a production server, the underlying operating system and hardware configurations clash, the environment fractures, and the model crashes. For years, the standard software engineering solution to this isolation problem was the virtual machine. If the environment was fragile, you simply packaged an entire virtualized computer around it. Docker solves this problem by eliminating the heavy virtual machine entirely. Instead of virtualizing the hardware, Docker shares the host operating system kernel and virtualizes only the application layer. To see how this works, we are going to build a reproducible Docker architecture from the ground up. We will start with the mechanics of single images and scale up to orchestrating multi-container machine learning deployments. Mastering this system takes a brittle local Python script and converts it into a universally portable production-ready artifact. To understand Docker's efficiency, we have to look at how traditional virtual machines process resources. This graphic illustrates the standard VM stack. On top of the host hardware and host operating system, a hypervisor manages a completely separate guest OS kernel for every single application. That means loading gigabytes of redundant operating system data into RAM, leading to massive resource bloat and slow cold start times. Now look at the Docker architecture on the right. Docker bypasses the hypervisor, relying instead on a streamlined client-server model. When a user types a command into the Docker CLI, it travels through a REST API directly to the Docker daemon, which operates as a background service on the host machine. The daemon takes over from there. It natively manages the images, the active containers, and the network routing by communicating directly with the existing host OS kernel. By stripping away the need for a guest OS, a single machine can efficiently run dozens of isolated models and their exact dependencies simultaneously, without maxing out system memory. This diagram represents a Docker image. It is a static, read-only template containing your application code, your libraries, and a stripped-down base operating system. A Docker container is the isolated, active running instance of that specific image template. Notice how the image is built in separate layers. If you spin up multiple containers that require the exact same base OS or Python layer, Docker caches that layer and shares it across all instances, saving massive amounts of disk space. When you execute the Docker run command, the daemon duplicates the read-only blueprint and adds a temporary writable layer right on top. The running application operates exclusively within this ephemeral writable layer. It can process data and execute logic, but it cannot permanently alter the underlying read-only image. Because that foundational image is strictly immutable, every container spun from it inherits the same starting state, providing a predictable environment across different hardware. To construct that immutable image, we use a Docker file. This is the exact line-by-line instruction manual the daemon reads to assemble the layers. Looking at this Docker file snippet, the very first instruction is the from command. This defines the foundational base layer. For machine learning, we strategically specify Slim or Alpine Linux distributions here. This excludes unnecessary system utilities, keeping the final image size strictly minimal. Next, the workdir command establishes the internal directory path where the application will live. The copy command is then used to transfer local assets, like your app.py script and requirements.txt file, from the host machine directly into the sealed image. To load dependencies, we use the run command. This triggers build time executions, such as a pip install, baking the libraries permanently into the image layers. This is distinct from the cmd command. cmd provides the default instruction, like flask run, which executes only when the container is finally initialized at runtime. We also use the env command to inject configuration variables, or host IP addresses, ensuring we don't have to hard-code sensitive data into the script itself. Historically, setting up a deployment environment required a sprawling internal wiki. Now that entire process is codified and version-controlled in a dozen lines of text. Once the container is running, it follows a strict operational rule. By default, it is 100% isolated from the host machine and from any other container. To route external traffic into a containerized Flask API, we use port binding. This diagram shows how we open a specific port inside the container and map it directly to a designated port on the host machine. But that strict isolation presents an issue for data. Because containers are ephemeral, if an ML container crashes, any internal data it generated during runtime is permanently destroyed. The architectural solution for data persistence is using volumes and bind mounts. Notice how this tethers a directory inside the container to a folder that lives safely on the host machine. This ensures massive training datasets or newly updated model weights remain permanently stored on the host's hard drive, while still being instantly accessible to the containerized model. Ports and volumes safely puncture the application layer's isolation, allowing network traffic and data to flow precisely where needed without corrupting the sealed environment. Production machine learning architectures are rarely single applications. A predictive Flask API usually requires a Redis cache to process requests and a persistent database to store the logs. Manually running, configuring, and networking multiple separate containers through the command line is fragile and prone to human error. To solve this, we use docker compose.yaml. As shown here, this is a declarative tool that lets us define a multi-container architecture in a single unified file. Docker Compose automates the synchronized build process and port mappings for the entire tech stack simultaneously, triggered by a single up command. It also establishes an automated internal network. The Flask container can securely resolve and communicate with the Redis container using just its service name, bypassing manual IP management entirely. With Docker Compose, environmental reproducibility scales up from a single application to a fully interoperable microservice ecosystem. We have replaced the resource-heavy virtual machine with lightweight containers that virtualize only the application layer. We have taken a complex machine learning environment, codified it precisely via the Docker file, and orchestrated it securely via Docker Compose. These immutable blueprints can then be pushed to an image registry, like Docker Hub, for global distribution. A server halfway across the world can pull that exact image and initialize it, reproducing the developer's local environment. This portable artifact can now be injected into CI/CD pipelines, scaled via Kubernetes, or deployed to any cloud provider while preserving the core application environment. By adopting Docker, machine learning engineers eliminate deployment friction,